Hi students. Okay, in this video we are going to talk about work, energy and power. This particular chapter is actually our last chapter for the year, and you will need to know quite a number of things from this chapter, but do not be afraid. If you follow this video closely and create your own notes, you should be able to understand it very quickly. Okay, for this chapter we have three components: work, energy and power. Okay, let's start off with energy, because energy is something that you already know quite well for most parts of it. Okay, so let's start with energy. So energy comes in many forms. So I believe you have heard about quite a number of them. One of them being gravitational potential energy. Okay, the other would be kinetic energy. Okay, there are others, okay, like thermal energy, electrical energy, and many more. Okay, so for this chapter, we are not going to talk about electrical energy, we are not going to talk about thermal energy, we are going to talk about these two in particular. Okay, so let's start from kinetic energy, because kinetic energy is something that is easy to understand, because it's actually very related to movement. Okay, so why do we say it's a movement? Because kinetic energy is actually energy due to movement. And it has a formula. Okay, it has a formula, and the formula is actually half mv squared. So what is Ke half mv squared here? Okay, Ke is actually our kinetic energy. Okay, m you already know is mass. Okay, unit is in kg. V is actually our velocity or speed. Okay, so what are we trying to tell you here? Okay, basically in order to calculate kinetic energy, you need to know mass and the velocity or speed. Okay, if you do not know any of the components, you won't be able to calculate the kinetic energy. Okay, so for velocity and speed, the unit is meters per second. Okay, mass is in kg. Yeah, so example. Okay, I just do a very quick example here. Okay, ball rolling on the surface at 3 meters per second. Okay, mass of the ball is maybe 2 kg. Okay, find the kinetic energy of the ball. Sorry, do you think you can find out what's the kinetic energy of the ball? Okay, for those who are already done, okay, you should be able to get something similar like this. Half mv squared, half times 2 times 3 squared. Okay, remember for us, we always talk about using 2 significant figures or more, okay, or 3 significant figures. Okay, so if you compute it correctly, you should be able to get 9.0 joules. Okay, so what is joules here? Okay, joules is actually the SI unit for kinetic energy. Okay, and it's a very special unit because everyone will be using it as a reference. Okay, so now that we know how to calculate Ke, let's talk about gravitational potential energy. Okay, for gravitational potential energy, okay, it's actually the energy due to height from the ground. Okay, so what do we mean by due to height from the ground? Basically, if anything is above the ground, okay, and there's a difference in height from the ground, okay, then there will be gravitational potential energy. Okay, the short form will be usually written as GPE. Okay, so formula will be mgh. Now if you look at mgh very carefully, okay, GPE here represents the gravitational potential energy. Okay, and is also given by the SI unit of joules. M is the mass of the object again. G here is actually our gravitational field strength. Okay, on Earth, okay, this one is very special, okay, so I'm going to put a star here. On Earth, okay, G is actually equals to our very special number, 10 newtons per kg. Okay, height, H is actually the height. Okay, height is measured in meters. Okay, so knowing this is actually two very straightforward energies. Okay, so I will give you one example as well for this. Okay, let's say the ball is raised up to a height of 2 meters. Okay, and the mass is 4 kg. Okay, find the gravitational potential energy of the ball. Okay, maybe you want to try this on your own now. Okay, if you have done, okay, it will compute out as this way. GPE is equals to 4.0 times 10 times 2. Okay, why is there a 10 here? Remember, G is actually our gravitational field strength. Okay, so if you do it correctly, you'll notice that it's actually 40 times 2, which is actually 80 joules. Okay, so the ball has gained 80 joules of gravitational potential energy. Okay, so these two are very straightforward formulas. Okay, and I hope that you were able to understand it very quickly here. Okay, so now we'll move on to work done. Okay, so work is the other component that we are talking about for this chapter. Okay, for work, is actually the short form of work done. Okay, it's actually a form of energy as well. Okay, think of it as the energy used to do work. Okay, and work here is very special. Okay, when something is doing work in physics, it doesn't mean that you will be perspiring or very tired. Okay, sometimes even if you perspire and being very tired, okay, you may not be even doing work in physics. Okay, so how do we know when we are doing work? Okay, so let me give you two examples. Okay, first, okay, I have a person holding a box. Okay, with his weights here, W. And I ask the person to move to the right. Okay, so how far did the person move? The person would move maybe 3 meters. Okay, compared to another person who actually just lift up the same box, okay, from this height up to another height up there, 3 meters as well. Okay, so which of the cases has work been done? Okay, what do you think? Okay, for science or for physics, this first situation, no work was done. In this second situation, work was done. How did it happen? Okay, so let's go back to the formula for work done. Okay, so work done here, okay, short form is WD. Okay, work done here is defined as the product of the force, okay, product of the force and its distance traveled. But there's a special condition for the force and distance. Okay, I'm going to list out the things as well. WD here is actually work done. Okay, and work done is a type of energy as well, so the unit is in joules. Force is measured in newtons. D is the distance traveled. But there is a very special condition, okay, for the distance. Okay, and what is the condition? Distance, okay, must be parallel to the force applied. Okay, so if you look at the two cases again, okay, in this case, the weight of the object is pointing downwards, but the box is traveling to the right. So in this case, the two forces are not parallel to, the force is not parallel to the distance traveled, hence there is no work done. But if you look at the second situation, the force is pointing down, but the box is traveling upwards. So if you look at this situation, the force and the distance are parallel to each other, even though they're opposite in direction. Okay, and this would mean that work is actually done. Okay, so I hope you understand this simple analogy. Okay, so let's try out something over here. Okay, here's an example. Okay, I have another box. Okay, there's being pushed with a 30 Newton force, and it has a weight of 20 newtons. Okay, the box will travel a distance of 25 meters. Okay, so the box will travel a distance of 25 meters. Okay, so what is the work done by or on the box? Okay, so can you try this very quickly? For those who are ready, okay, work done is equals to force times distance. This is our formula. But if you look at this particular question, we got two different forces. So which force are we going to use? That's right. Okay, it must be the force that is parallel to this distance. So if you look at these two forces, there's only one force that is parallel to this distance of 25 meters, and that will be the 30 Newton force. So the force that we require down here will be 30 multiplied by 25. Okay, if I take 30 multiplied by 25, I believe I will have 750 joules. Okay, so any problems? Okay, just think back about what is actually work done here. Okay, so work done this formula F times D, and D is very special, is the distance that is parallel to the force that is being applied. Okay, but you also notice that this this formula for work done looks very similar to another formula that we have learned earlier. Okay, do you know what it is? Yes, okay, it does look like the one that you have learned in turning effect of a force or moment of a force. Okay, and for that chapter, okay, the formula is also, the moment of force is also force times distance. But in that case, the distance is the distance that is perpendicular to the force applied. So it's slightly different. Do know what is the difference between the two formulas. Okay, so far we have learned 3 different things: gravitational potential energy, kinetic energy, as well as work done. Okay, I hope you have learned something from this chapter, okay, from this simple video, and hopefully this video will help you in your learning.